Thank you, everyone, for inviting me here. We were here 3 years ago, loved it here, and it's a delight to be back, and I see you all. How many of you are ready for a technical talk to kick off the conference? I mean, a technical talk with code, and I'll give you all the code, working code, some of which you can start to use right away. Is that better? Okay, good enough. How many of you have already used Python's abstract base classes? How many of you used the ones in the collection module? That doesn't compute at all. So that is one of the most important sets of abstract-based classes. And so since you're mostly familiar with them, I'll do the beginning part of the talk where I go over the mechanics and do it somewhat quickly. My understanding is that there will be a test afterwards and that they're giving a question out, and I was supposed to supply an answer. So make sure you pay attention to every detail. Fair enough? Are you ready to rock and roll? All right, here we go. Hi, my name's Raymond Hettinger. That's this part right here. If you want to tweet right now and say that this is an enjoyable talk, this is a place to do it. If you want to watch some of my training videos, they're mostly free to you online through Safari Online. There they are. That's my company, and here's what we're doing. Abstract base classes. What are they all about? So ABC stands for Abstract Base Class, and I'm guessing you all already knew that. What most people have a hard time articulating is what exactly are they for? It is a form of communication between subclasses and parent classes. Why do we subclass? The answer is subclasses let us reuse the code from another class. So they have to talk to each other. So why do we need abstract base classes? We have three purposes. The parent can communicate to a subclass, here's the structure I demand of you. Secondly, a class can identify itself as, hey, I meet those requirements, I can work with this parent. And there's an enforcement mechanism built inside to check and make sure that we meet those requirements. So we'll start with a example ABC. Okay, and this one is an entertainer class. In order to build an ABC, you import from the ABC module and inherit from ABC. Now this looks like regular inheritance, but underneath the hood there's some meta-class magic going on. And the abstract method is a decorator to mark the abstract methods. So to be an entertainer, you need to be able to do two things. You need to be able to sing and dance. These are not concrete implementations, they're abstract implementations, which means that we've defined the code as pass. It doesn't actually do anything. So this essentially specifies what are the requirements of being an entertainer, but it doesn't tell you how to be an entertainer. I've got some instructions on the bottom for how to build an abstract base class, but roughly it's this: import this, inherit from the ABC, and take the abstract methods and mark them as such. One of the nice things we can do with an existing ABC is ask it, what are your abstract methods? This is important if somebody else is giving you the ABC class and you need to know, what is it I need to implement? Sir, I'd like to become an entertainer. What do I need to do? Well, you need to be able to sing and dance. So how do we identify a class as implementing the entertainer ABC? One way is through registration. So this class is a street performer. It's a concrete class. It actually knows how to do things, and it actually knows how to sing and how to dance. In order to mark it as fulfilling the requirements of entertainer, you can register it. This has a really interesting effect. In every other language I know, is instance and is subclass checks to see if you're an instance or if you're a subclass. But ours does something special. It will also check to see if you're registered as a member of this class. So if you claim to be an entertainer, there's two ways to do it. You can actually be an entertainer, or you can claim to be an entertainer. Okay, and here's how we make the claim. This we will register ourselves as a street performer. The effect of this is if you make an instance of street performer, it is now recognized as an entertainer, even though it didn't subclass from that. Everybody got registration? How do you make yourself an entertainer? Register yourself as such. There's another way. You can subclass entertainer. This will also inform is instance about the relationship. And so if we want to know if the lounge performer is an entertainer, it returns true. In this case, is instance is doing exactly what you expect. It's identifying a member of a subclass. The interesting contrast between the two ways is that subclasses have an enforcement mechanism and registration doesn't. So here's a wannabe performer. Sure, the wannabe performer knows how to sing, but doesn't know how to dance. It does not. It's not a real entertainer. So if we make an instance of wannabe performer, it refuses to instantiate. It says, you can't be a performer because you don't know how to dance. This is fantastic. Which raises the question, what happens if we try the registration way instead of the subclassing way? So here's a wannabe performer not subclassing from entertainer. It registers itself, and then we go to make an instance. This time it does make the instance. Not a good instance, a broken instance. We ask if it's an entertainer, and it says that it actually is. Is it really an entertainer? It doesn't know how to dance. Okay, there you go. Just checking to make sure that you're all dialed in. Remember, there's a test afterwards. So if we ask it to sing, in fact, it can sing an amateur version of the national anthem. If we ask it to dance, it can't dance, even though it's registered as an entertainer. In other words, you get to do something very interesting with registration. You can lie to is instance. You don't actually have to be an entertainer to be registered. So without subclassing, there's several differences. The registration always succeeds, even if you're not a real entertainer. The instantiation succeeds always, even if you're not a real entertainer. And is instance will claim that you're an entertainer, even if you're not. And at runtime, the method fails. So there is some danger in the registration method. You actually really want to make sure that you implement all the methods because it has no way to check for you. Who learned something new? All right, fantastic. So here's some summary and comments. Why do we do abstract-based classes at all? It's to formalize a relationship between the parent and the subclass. Everything that we've done so far could have been done without abstract-based classes. We wouldn't be able to do an is instance check later, and we wouldn't be able to verify that all the proper methods are there. So think of it as a way of formalizing the relationship. You've learned how to do it, which is inherit from ABC, and mark the subclass contract with abstract method. How do you make it recognizable by instance and subclass? There are two ways. You can subclass the ABC or you can register it. The advantage of subclassing is instantiation is blocked if one of the methods is missing. If you don't know how to dance, you're not a real entertainer. In other words, the enforcement mechanism works. You've also learned for registration, there's no error checking, and in fact, you can lie to it. The alternative to lying is you make a mistake, and it doesn't point out the mistake. And you've learned to introspect ABCs. You can ask it, what abstract methods do you require? What is needed to become an entertainer? Singing and dancing. And you've learned how they're implemented. ABC is implemented with metaclasses, and abstract method with decorators. Here's an interesting fact that is a widespread point of confusion. ABCs are not recognizers. People see this is instance and say, is this lounge performer an actual entertainer? And they think that more verification is going on than actually takes place. And all they can do is check and see if something is a subclass or if it is registered. But if something's not a subclass and not registered, even if it knows how to sing and dance, it might not show up as an entertainer. And so people are continually disappointed about this. They make bug reports all the time and said, I made an entertainer by a class that could sing and could dance, and yet it didn't pass the is instance check. There are two ways to do it. You can register it or subclass it, but it cannot recognize an entertainer without having seen it first. Are ABCs recognizers? No, you have to register or subclass. And one of the interesting things about the limitations of ABCs is they just check to see if the required methods are present. It doesn't check their signature, it doesn't check to make sure the methods work or that they do the right thing. In other words, it's a very limited form of checking. Congratulations. If you learned everything in the summary points, you are now masters of abstract-based classes, and I can consider myself done, and goodbye. I've got time left. Okay, here we go. Strategies for using abstract base classes. There are 3 ways to use them. You can make a pure abstract class, and this is what will be familiar to you if you come from a language like Java or C++. In those languages, abstract base classes are fully abstract all of the time, and they do nothing else for you other than specify a formal relationship. And so you don't get any extra firepower from that. However, in Python, we use them in 2 other ways as well. One of them is called the framework design pattern, and the other is mix-in classes. And the message I came to bring you today is we've got some mix-in classes for you. You don't have to write them yourself. They're very powerful, and they do a lot of work for you. Are these good characteristics? Things that are powerful, do a lot of work for you, are already tested, and take very little work on your part. So a pure abstract class is something like our entertainer class. It's pure in the sense that there's only abstract methods and no other services. So this is the kind of thing that you get in Java. In other words, we have a definition of what an entertainer is, but we don't have an actual entertainer. The more interesting one is the framework design pattern. By the way, I've got these sections at the end called extras. They are working code for these frameworks that I'm about to show you. They're code that I've written myself, but they are ready to use, and they're pretty darn neat, and they're fun to play with, and they have practical uses as well. So in a framework pattern, the parent is smart. It manages the execution flow. And the subclass is like a worker who reports to a boss that has some specific capabilities. But the boss is in the parent class. The parents rule, the children do what they're supposed to, and you put your children to work. It's a very simple arrangement. How do you like that arrangement? Those of you who are parents like it. Those of you who are children, not so much. All right, so the parent class in this case is puzzle, and the child class is stepper. So what does a stepper have to do? It defines a position, it defines a goal state, and an iterator that shows possible moves that for getting there. An iterator takes the current state and generates a new state. Now this little bit right here, what it does is shifts the one space to the left. What this does is shift one space to the right. So the 1 can move left and right. This is a very simple puzzle. If all you can do is left and right, how do you move the 1 over to the right? And the answer is a series of rightward moves. The interesting thing is how we solve the puzzle. The child defines the current state, the goal state, and possible moves. The parent figures out how do we get to how do we figure out the solution? So we call a solve method. Do you see a solve method in the stepper puzzle? No, where does it come from? The parent, which is smart. This is called the framework design pattern. In the framework design pattern, parents are smart and children provide the concrete methods, and they are the slaves in the family, as it ought to be. Simple thing. There's another way. By the way, this code for puzzle, I put a simple toy puzzle here. Let me skip ahead to my puzzle framework. It's got instructions for how to use it, including canonicalization and symmetry arrangements. This is the entire puzzle class, including the smart parents solve method. Down below, though, I have lots of interesting puzzles. A jug filling puzzle with nice cute GIFs that go along with it, 8 queens puzzle, triangular T puzzle. There's a lot of puzzles in here, including some puzzles that are hard. This is the first one that's hard. I have never seen a human being ever able to solve this puzzle manually. It's a famous puzzle in my family. It was at my grandfather's house, so I called it Paw Puzzle. And I saw many engineers come by and visit our house, pick up the puzzle, play with the puzzle for hours, and not be able to solve it. I know of only one person on this planet who was ever able to solve this puzzle. Who is it? That was me. How did I do it? I wrote a program to do it. I wrote it on a TRS-80 in BASIC a long time ago, but it is basically this program in Python. And once I saw the solution, I figured out how difficult it was. What happens is the solution space gets very wide, then very narrow, And it's all a big circle, but there's an exit door. And if you recognize it, you can go to another level, another group that fans out and backs in. And there are two thin little doors on the way to the solution. And if you don't find the door, you stay trapped in a space that has no solutions in it, and you can play with it for hours. So this is a somewhat hard puzzle, but you get the idea is, how do you make a puzzle solver? You define the puzzle with a starting state, an iterator that generates possible moves, and some ability to recognize what a goal state is. After that, all of the work is done by the parent. This is called the framework design pattern. So I've given you a framework that I wrote. Now, mix-in classes are somewhat different. In that case, most of the intelligence is in the children. They provide a almost complete working class. However, the parent provides extra capabilities that layer on top of what the children already know how to do. So they augment your capabilities. So here's an example, a child class called calculator. It does something very simple. It stores a factor, and then it multiplies a value by a factor. It is a complete standalone class that would work fine by itself. But we inherit from a mix-in class. The mix-in class says we have an abstract method, calc. And what show does is it doesn't actually touch the underlying factor or data. What show does instead is it calls that calc function. So the characteristic of mix-in classes is they depend on the child implementing some particular methods, and if they're present, it adds a new capability. So here's an example of how to use it. I make a calculator that can double results. I call a calculator M5, and it doubles it and shows 10. Can you see the output from this line? No, it's invisible, which makes it hard to debug. There's a better way. The better way is to call the show method. Does calculator have show? It does not. So it inherits it from the visible class method, and visible calls calc and then shows the inputs and outputs, improving your ability to debug. This is a simplistic example, but there's an enormous amount of power here. The idea is that once you've written visible, you can use it on any class that has a calc function on it. And so we could end up with a small library of mix-ins, and these mix-ins could take your existing classes, and you can add new capabilities simply by naming the capabilities that you want. So we've heard of object-oriented programming. This is checklist-oriented programming. Once you've made the basic functionality, you just say, I'd like to take this class and make it visible and persistent and self-documenting, and add in some other capabilities, and you simply list the ones you want, and the mix-ins do all of the work for you. So this is a very high payoff activity, especially if somebody has written the mix-in classes for you. So framework design pattern is pretty cool. You extend an existing class and provide the details of a method. You essentially customize it. But this is the one that I really like, the mix-in methods. They're wonderful because if you have a library of them, you can get an enormous amount of work done simply by inheriting from those classes. So let's put it together for something non-trivial, the collections ABCs. So this is a very rich group of mix-ins in the ABC module. Why do we like them? It takes very little work on your part to implement a new collections class. And then the mix-in supplies lots and lots of other methods that are otherwise a pain to implement. This is a huge time saver, but more than a time saver, these methods that you're bringing in have already been tested. So when you add them, you name the extra capabilities you want, and you get a lot of firepower for free. This is one of these tools that if you take the time to master it, play with the code that I'm going to give you, it'll amplify your capabilities enormously. You've heard of the myth of the 10x programmer. It is, in fact, a bit of a myth of a 10x programmer that one person is always 10 times more productive than another. On the other hand, some programmers know about power tools like these things, and they know how to just import the things they need and attach them rather than writing them from scratch. And that gives you more than 10x leverage. Also, you get high reliability out of it. So what is a sequence? It's a generic term for a resizable collection that's ordered, indexed, and sizable. You saw before, we can find out what the abstract methods are. All you need to implement a sequence is the length and get item. All you need for a mutable sequence is length, insert, get item, set item, and del item. This is very little work on your part. If you want to make a sequence, implement 2 methods. What do you get for free from the mixin? It writes all of these other methods for you. And for a mutable sequence, you automatically get all of these methods. So you get about 11 of them for free, which is fantastic. Likewise with sets. What are sets? They're like sets in mathematics, and they support membership testing, set-to-set operations, union, intersection, difference. They're all about data analysis. And we can see what their methods are. Only 3 of them are required to implement a set. This is very little work. And they automatically give you all of these other set methods for free. That's where all of the interesting logic comes in. And then mapping. So a mapping is a generic term for anything that's like a dictionary. Only 3 methods for a mapping, and for a mutable mapping, a total of 5 of them. And then here's all the things that you get for free. This is an enormous labor saver. So here's an example, a list-based set. Regular sets are based on hash tables, and they require hashable objects. But perhaps you don't want that. Perhaps you have unhashable objects. Well, we can change the underlying data store from a hash table to a list. So the list-based set has an init that says save all of the elements in a new empty list. Now, how do you get the elements out of a set? You iterate over the underlying list. How can you tell if something is in the set? You look to see if it's in the underlying list. How can you tell how big the set is? You ask how big the underlying list is. The interesting part of this, the part that makes it all work, is when we put the data in to begin with, we make sure that that data is not already there. Interestingly, not in just calls this contains function. So one of the neat things about building this is if you have an underlying data structure with some rich methods, you can already use those methods. Here, we're taking advantage of the fact that list already implements most of the methods we need, and this is close to being a straight pass-through. So here's how we use it. Make a list-based set of this one and this one that calls the init. It eliminates the duplicate elements inside and stores it as a list. The interesting thing is we get for free this thing, the ampersand, the AND operator, and it tells you exactly what members of each list are corresponding list members. So it tells you there's an overlap of the letters D, E, N, F. This is 4 lines of code, 5, 6, 7 to implement a complete set. Who thinks that's kind of awesome? 7 lines of code, complete set, all of the set methods, and all of the interesting methods are already tested for you. The only thing I don't like about this example is it doesn't suggest the full power of how far you can go with this. So I built a few for you of things that I have used in production code. I've simplified them a little bit just so they can fit in a short presentation. But let me show you some cool things that can be built very, very quickly using these tools. So the first one is a bit set. So regular sets are based on hash tables. And hash tables are sparse, and they're kind of big, and they don't store the data in the hash table. We have references from the hash table to the underlying data. And so it can take a lot of space. So this is our alternative. It only works on integers that are in a fixed range, but it stores them as an array of bits. So what is its superpower of this set? It's much more compact than a regular set, and so it will scale to fairly enormous sets. This computer has 16 gigabytes of RAM, a byte being 8 bits, so 16 times 8 is the number of bits. That's the size of a set I can store in RAM on this without going swapping out to a disk. So that's a pretty massive capability. So what's necessary here? Well, we set a limit on our range. How big of an integer can you put in here? And we make an underlying byte array. So if you want to store 800 bits, well, we need a byte array of size 1,000 in order to do 1,000 times 8 gives you the 8,000 bits. This operation here just rounds up and says, if I only want to store 20 bits, it still takes 3 bytes to store it because we need some for the leftover. So how do we locate a bit? It's with simple bitwise operations. I use divmod 8 that tells me if I want bit number 1000, then that's going to be at a byte, 1000 divided by 8, and then the modulo 8 tells me which bit number it is. So for this will locate the particular bit you want. So if we want to know if a bit is in the array, we find the byte number and bit number. We look up the byte, shift into place the relevant bit, and it with 1, and it tells us whether the bit is stored. Addition is also a little bit flipping. It takes a mask for the bit number and R's it on to the appropriate byte. And discard does exactly the same thing, but it ands with the inverse of the mask. So this is bit flipping operations, something that everybody used to know before the year 2000. It made you a real programmer. After the year 2000, it's mostly an unnecessary skill except for this particular context. Building an iterator over it is not difficult. And getting the size, I just loop over our iterator and count the number of bits that are 1. Not all of these methods are required by the abstract base class. It doesn't require a init, but if you want data in there, you're going to need an init. Repr is not required unless you want to look at it. But these other ones are the required methods. If you implement those 5, you get the set logic for free. Now here's an interesting wrinkle in this. Along the way, when you do set operations, you have to build new sets. And the abstract base class doesn't know how to do that. So we provide this underscore method called fromIterable. And its job is to take anything you can loop over and build a new instance of this class. And the reason that's important is there's no way the abstract base class can know that we have to pass in a limit. Okay, there you go. Pouty lips, show some, okay, there you go. All right, bit set. Let me switch over real quick. Get the bit set. So we have the code over here on the right side. I'll try and make the type as small as possible so you have no chance of seeing it. Okay, and from bit set, import star. Make a instance of a bit set. And what does it need to know? It needs to know a limit. My maximum number will be 100. And iterable, so I'll pass in some data, 20, 30, 40, 60, 75 are members of the set. I can immediately ask questions like, is 20 in the set? That is true. I can make another bit set T that has the same range. And we'll put in 20, 40, 75, and 93 and 97. Favorite prime numbers, okay. And we can compute the union, intersection, and difference between the sets. Keep in mind, I didn't write any of these methods. Where did I get them all from? Where did I get them from? All of that work was done by the mutable set. The underlying data store here is in the data, and that is a byte array. And if we list it out, you'll see the numbers that are stored in the byte array. These don't look like our original numbers because each one of those is a bitmap. For instance, I can take 16 and show it in a binary, or 64 in binary, and you can see one of the bits is set in that particular byte. The important thing here is the size of that data. Lin, that is a set of up to 100 elements only stored in 13 bytes. This is a big win because the size of an empty set in regular Python is already several hundred bytes. Okay, so that's a huge win, 20 to 1 space savings, and it takes very little effort. So this code I have used in production more than once. I'm giving it to you. I hope you have fun with it, and I hope I've convinced you of the power of abstract base classes. Michael, they applauded. If I was smart, I'd get off the stage now. All right. Your file system is a dictionary. How do I mean by that? In a directory, you have file names, these are keys, and the contents of a file is a value. So a problem with regular dictionaries is they're in memory, which means you can't inspect them while they're running. And if you turn off your Python process, they die. They're not persistent. And they can't be shared with other programs, and you can't look at them as a text file while they're running and inspect a program while it's running. And you can't change data in a running program in a dictionary. This is terrible. There is, in fact, a better way, a file dictionary. And I don't have time to do all of a file dictionary, so what am I going to use to get the work do the work for me? Mutable mapping. All right, so when I create a file-like directory, or a file dict, I pass in a directory name, and it builds a directory for me. What does getItem do? It says take the directory name and the key, put them together, and it looks for that as a file name. It opens the file, and whatever data is inside is the value. Now we transform file not found errors into key errors because that's what dictionaries do. SetItem looks for that file and writes it. And writing in a W mode instead of an A mode, it'll overwrite an existing value just like in a regular dictionary. Delete item is fairly simple. We can do an OS remove, but if the file's not there, we raise a key error. Length is pretty easy. We list the directory, and however big the list is the entire size of the dictionary. And this iterator, all it does is iterate over the file names. And the repr just shows you all the items, which is interesting. This is called self.items. Did I write self.items? No. Where did I get it from? Mutable mapping. This is 100% of the code necessary to write a file dictionary from scratch. I'll go ahead and create one from file dict, import file dict. And over on the right, show the source code for it, hcat file dict. That's the code that we just looked at, which is why it's small. The dictionary will be Starks, of whom there are not as many anymore. Okay, and the directory for it will be Starks. And then I can add in Starks, Arya, Tomboy, Starks, Sansa, Bad Taste in Men. Okay, and Starks dot keys, Starks dot values. Keep in mind I didn't write these methods. I got them for free. Starks, look up Arya, which raises the question, how did all of this work? There is a subdirectory now called Starks. That has Arya and Sansa in it. And if you look at the contents of them, it says that Arya is a tomboy. Let's edit that outside of Python. I want to show that this is something that we can change. And instead of tomboy, let's put out Ice King Slayer. Then over on the left, in the still running process, look up Arya, and you see that it changed. We'll want to clean up line endings and whatnot, but you can have dozens of processes running, all sharing this directory, which means that they're sharing a dictionary. You can look at the dictionaries while it's running and modify it while it's running, and if I kill the Python process, it's still there. Presto, a persistent dictionary that is shareable and concurrent. Who thinks that's awesome? Who thinks it's kind of a hack of a file system? You demand a better way. Raymond, I need something more official. How about the underlying data store is SQL? So this is exactly the same code, except this time our init creates a database name, and it creates a table with key values store and a unique index. So a set item does an insert into the dictionary. Get item does a select a value where the key matches. A del item does a delete. Length is a select count star, and an iterator is select all keys from the dictionary. I don't think I need to demonstrate this one because it works almost exactly the same way. It has some really nice benefits for doing it this way. One of the big benefits is it's stored in one file. So after you've used this dictionary, you can email this dictionary to someone else. They can use it, modify it, and email it back. You can share dictionaries as easily as you can share spreadsheets. Who thinks that's kind of awesome? All right. Have I gotten the message across that abstract-based classes are great? They're fantastic, and particularly the collections ABCs, they are something that you really want. I'd like to wrap up with one last framework. This is a data validation framework. This part is a subject of another talk, a descriptor talk, and the idea is anytime we store a variable for a validator, we're going to store a private name for it. Anytime we look up the variable, we look up the private name. No magic. And anytime we set a variable, we store it to the private name. The part that's special is before we store it, we validate the variable. And the validation method is an abstract method. This one does nothing. So you can't instantiate this validator class. So how do you use it? You subclass it, and so one of is one that a validator, if we put in some options. The options are valid values are win, lose, or draw. And you store these as a set. What does the validate method do? It takes a value and it checks to see if it's one of the valid values. And it will preclude you from accidentally storing something into the database that is incorrect. And so I built several validators for you here. A number validator can make sure something is an integer or a float, check for a minimum value and a maximum value. String validator can check for a minimum size, a maximum size, some predicate like is it all uppercase or title case, and it validates all of these for you. The interesting thing is making new validators is quite easy. Subclass from a validator. The abstract-based class will check and make sure that you put in a validate method, and the whole thing is fairly easy to use. Do I have a couple minutes left? This is good. cd ... hcat validators, and let's pull up a one of validator from validators import star. You should never import star. What did I just do? Import star. Do as I say, not as I do. Okay. So class speaker. Person's name is a string, and the minimum size on the string is 3. And a person's age, integer. And for, is that called an integer class? No, we called it number. And we'll pass in a constraint, which is, let's say, max value is 50. Does this look a little bit like data classes and a little bit like typing name tuple? It does. This is a very old-fashioned technique. The first software I've seen that did it was called Traitlets, and then ORMs use a somewhat similar strategy. And topic will be constrained to, there's very few things that you can talk about here, and one of them is you can talk about Python, or you can talk about computing, or you can talk about having fun. No other topics are allowed. So you've got a speaker. And we go to store the name is I am 54 years old. Good or bad? Instantly detected, it expected 54 to be a string. So we'll put in the name is Raymond Hettinger. Raymond.age, 154 years old. Oh, no more than 50 is allowed. Okay, I'm actually not allowed here at all. Okay, so I'll put in my younger self, 36 years old. That is my actual age in hex. Okay, and it's validated. And Raymond.topic, I am here today to talk to you about Ruby. Not allowed. It must be Python computing or something fun in Python. So these are data validators. They're very easy to use. I've given you my abstract base class for it. All you need to do is subclass it and give it an init and a validate method, and it is ready to extend and put to work right away. It is a very, very powerful tool for preventing data corruption errors. Who learned something new? Wow. Did you have a good time? I did too. Thank you again for inviting me. It's an honor to be able to speak to this audience.
Any questions? Please raise your hands.
Thank you for the talk. Please explain why a registration method allows to register class that doesn't implement necessary methods. Why it doesn't throw not implemented error on registration?
So let me summarize the question and the answer briefly. The question, why? Answer, because. All right, his question was, why doesn't registration do validation? There is a very shallow but highly accurate answer to this question. Why is Python the way it is? Because Guido said so. So abstract base classes are implemented in a way that made sense to Guido at the time. And he had a wide variety of use cases in mind when he designed it. And so we try to not design in the abstract. We try and design to match use cases. And the particular use cases he had, it was sometimes useful to be able to lie to his instance. For example, you have some class that is checking to see if a sequence is given into it. Collections deck at the time has sequence-like behavior. It's indexable, but it was missing some sequence methods like remove at the time. However, if you knew that a particular function didn't use the remove method, it was okay to lie to that function and say, I'm giving you a deck, treat this like a sequence. So when you know that one of the required methods isn't going to be used at all, lying is sometimes helpful along the way. So I believe that was his rationale. I think he had some specific real-world use cases for it. And in particular, we knew that there were lots of existing classes that, of course, didn't inherit from this existing tool, and we're going to have to register. And in some cases, they didn't have a particular method. There's sequence-like behavior, but it's missing insert, or it's missing count, which is a method people don't often need, but is required by the API. So I would say it's use case driven. It's because Guido said so, because it made sense at the time. And what validates the decision? Until now, no one ever has complained about it in over a decade out of millions of users, which is a hint that Guido probably did the right thing. Great question. Next. Yes, sir.
Hello, Raymond. Great talk. Thank you very much. And I'm a great fan of abstract-based classes, and particularly the ones in the collections module, so thank you for that. My question is kind of similar, and you might just say the same answer as before, but I love abstract-based classes for the way they give us first-class interfaces. in Python, but there does seem to be some deficiencies compared to the concept from other languages. And the ones I particularly had in mind is that the validation doesn't do validation of function signatures, so you can provide a broken implementation and it will still pass validation. And the other question would be, why validate at instantiation time? Why not validate at class creation time? That Python provides the machinery to do that.
All right.
Okay.
All right.
I'll stop there.
So let me summarize the first question. What is the best way to connect a giraffe's heart to its lungs? Is it to go directly or to go all the way up through its neck and all the way back down? You might think direct is the right answer, but in fact, the giraffe has a artery that goes all the way up through its neck and all the way back down. What happened was at the time, early in the giraffe's evolution, the direct path was the one that was used, but it was below the neck bone. But the neck got larger and larger and larger over time, and that early design decision persisted. So in the case of abstract base classes, when they were made, they had some somewhat limited goals. We didn't try to solve all of the world's problems all at once. Are the required methods present? And by itself, that was a useful thing. It would have been nice to have extended it and say, do the signatures match and do the types match? Did we have a good typing system at the time? No, we didn't get a good typing system until basically right now. We've had typing for about 3 years, but it hasn't gotten good until fairly recently. So abstract base classes predate typing by a very long time. We also have signature objects available in Python now. They didn't exist at the time as well. I think signature objects are on the order of 6 or 7 years old, whereas abstract base classes are on the order of 12 years old, something like that. And so the tools necessary didn't exist. Also, when a person is building something like this, they have a class of problems they want to solve, and they're not trying to solve everybody's problems. And so this solved a particular set of problems Guido had at the time, and seemed to work reasonably well at that particular task. But over time, our needs have grown, so we've layered in a type system. In addition, sometimes you try to not solve all the world's problems yourself because somebody else might do a better job at it than you. And in fact, at the time abstract base classes existed, traitlets already existed. Traitlets are very much like the validator class I just showed you, and they are dramatically more powerful than typing. Typing can tell you something is a list or a list of integers. Traitlets can verify, is it a list of integers in a particular range that are all even numbers? And so you can layer in logic that is not possible in a regular typing system. In fact, the world is moving toward types that are smarter now. I think it's called dependent types and has magic words like homotopy and words I haven't learned yet to describe it. But the concept of traitlets was around for a long time. That was a dynamic runtime validation that could check a lot more than types. It could check signatures, it could check ranges, etc. And so perhaps this was a need that was not best met through abstract base classes. So at the time it was made, we didn't have the tooling for signatures, we didn't have typing, and we had a better tool, traitlets, that did a better job at that particular class of problems. Which is not to say that if we had it all to do over again and knew all known use cases, that there wouldn't be a unified approach, that we wouldn't have separately validators, traitlets, signatures, abstract base classes. They might be one common unified thing. So like that giraffe example, were we redesigning a giraffe from scratch, we might design a giraffe much differently than it's made, so it's safe for a giraffe to drink water, because the lions know to wait for the giraffe to drink water, and they come up, take one swipe at the neck, and then the giraffe is a goner. And so we can exploit this weakness in the system ourselves. And your second question was, why did Guido choose to do checking at the time of instantiation of the class? And one practical reason is Your subclass might not implement all of the required methods itself. It might implement a handful of them, and then you have a subclass to a subclass. Also, Python being dynamic allows us to, after the class is made, inject methods after the class, or after the class has been made. Some people feel that this is a little bit hacky, but it gives Python superpowers occasionally. It lets us do things that are very hard in other languages. So you don't day-to-day monkey patch your own classes, but once in a while, it's a really wonderful technique. In other words, we can't know when the class is defined whether all the methods need to be present. It is only when we instantiate by then they really need to be there, otherwise the class itself is not functional. This is particularly true because I believe, given where Guido was working at the time, they had dynamic class creation, and so users would specify methods that they want and they would populate on the fly. So I believe that was a basis for the design decision, certain practical considerations. That said, if I were designing this module, I probably would have designed it differently than Guido did. On the other hand, as I'd mentioned before, this module's been around for a long time. I've watched the bug tracker every day. Every single day. I look at the bug tracker, and I can assure you, since it's been created, no one has ever complained about it. And when you have millions of users and no one complains about it, either they're A, not using your tool, or B, they're completely satisfied. The truth is, in fact, somewhere in between. And it just may be that there's a limitation to the tool that in theory matters, but in practice doesn't seem to come up a lot. In other words, it doesn't seem to be a real world problem. Both excellent questions from Michael Ford, who will be a speaker later today, and somebody you really want to listen to, somebody with really deep real-world experience. More questions? Yes, sir. He needs a microphone. Oh.
I have microphone now.
Oh, okay.
Yeah.
Oh, you have a microphone.
Yeah. Thank you for your talk.
Yes.
Actually, sometimes using abstract-based classes is kind of overwhelming because you can achieve same behavior by just raising not implemented error in your base class function. So what do you think about that? It's kind of
I believe the question was, can you do without abstract base classes simply by having a parent class define a method that raises a not implemented error? Returning not implemented is a different thing. That's done for comparison operators. So raise a not implemented error. And in fact, this is something that was commonly done before there were abstract base classes. There's a disadvantage from that. It's not introspectable. And you don't find out until you've called the method, at which point it's too late, and creates a risk of a error in production for a method that never got called until one day someone did something exotic. But in fact, that is a perfectly reasonable approach, is design a method that will fail 100% of the time when you call it. Also, a problem with this approach, and we also use doc strings for it as well. We write in, you need to define a method that does so-and-so. But these things weren't introspectable. There was no way to programmatically go into a class and say, are you an abstract-based class? What methods do you require? So this defined an API. So we can actually ask now, what are the abstract-based classes? And we can say which ones of them have been filled out and which ones are left, and give very useful error messages. All of those things are difficult to do by returning not implemented. So like most things in computer science, there is a simple answer to the problem that works practically a lot of the time, but sometimes we throw a little bit more machinery at the problem and we get documentation, we get enforcement, we get the ability to lie to is instance if we need to, get the ability to ask a whole bunch of classes which interface the implemented. I'd like to do a second follow-on to a part of the motivating use case for abstract-based classes. I was originally, there was exactly one problem that got us started on discussing abstract-based classes. And I had a very different solution in mind that was as low power as your solution. And roughly the problem was this. In Python, you can make a mapping with a method called getItem. And if the getItem fails, it raises a key error. Or you can make a sequence that has a method under getItem. And if it fails, it raises an index error. And these two things behave very, very differently than each other. And we found all throughout our source code, particularly in CPython source code, it was often necessary to distinguish, is this object a mapping or is it a sequence? And if you check to see if getItem was present, it didn't tell you anything. You actually needed to know, well, what kind of getItem are you? So my proposed solution to the problem was to just put on an attribute that says, I'm a mapping, or an attribute that says, I'm a sequence. Sequence is true. How do you know if something's a sequence? Just ask it. It'll tell you. How can you tell if there's life on Mars? It's easy. Ask a Martian, and even if they say no, the answer is significant. So I proposed an attribute. Guido was driven more to this style based on his experiences, I believe, in Java. And at first, I was opposed to it because I thought, boy, that's a lot of machinery just to throw at just solving the problem. Are you a mapping or are you a sequence? What made me really happy with the result, though, was we got more than an identification of which is which. We got the mix-in classes, and that was a huge win. The other win that we got out of it was prior to abstract base classes, these words I've been using like mapping and sequence were thrown around randomly without precise meaning. So when one person said sequence and another person said sequence, we weren't necessarily talking about the same thing. Now when we say the word sequence, we mean precisely that it is sizable, indexable, ordered, that it has a count method, a remove method, etc. And so making these abstract notions precise was also a big win. In a way, it's the same as true of the typing module. Even if you never use MyPy to validate the typing in your module, the fact that we have a language now to describe this is a dictionary whose keys are a string and whose values are a tuple that consists of an integer and a decimal was something that we used to say very loosely in comments, and people would say it in different ways. It was hard to identify. We now have a precise language for describing types. So abstract base classes were a win there too. So even if you never use ABCs, you've gotten a small victory because we know precisely what is meant by a mapping. By the way, do you know the name of my training company?
Sorry.
Oh, you missed that at the beginning in the opening slide. It's called Mutable Minds. What is the one thing I need to be able to teach people? Do I need a projector? I do not. Do I need a computer? I do not. What's the one thing I need? Mutable
Mine,
minds. And once in a while when I teach a class, I get a room full of people with immutable minds. Okay, so I've defined an abstract base class, immutable minds. I've named my company after the ABC. And what do you need to be teachable? A mind that can be mutated. If you're open to new thoughts, we'll do great. Did that answer your question, sir?
Yeah, thank you.
Okay, fantastic. And you?
Thank you for a wonderful talk. I've seen several techniques to write a body, to implement a body of method marked as abstract, to write a pass string, to raise a non-implemented error, or to write some default and simple implementation just for demonstration. What is your opinion? What is the most preferable technique to do it?
Can you take one more crack at the question? I didn't catch all the parts.
When you mark a method and as an abstract, you need to write something in the body of a function.
Okay, I've got it.
Yeah.
Okay, so when you define something as an abstract method, it cannot be called because you can't instantiate the class. So in a way, how you define the method is irrelevant. All that has to match is the function name. Interestingly, you don't even have to have the word self in it for it to work because it will never be called. That said, Guido was not only the creator of abstract base classes, but also its first user and made our first examples. So he set a pattern for us. And the pattern is put the signature in of the actual function that you're going to use, because you're essentially laying out a blueprint for somebody who's going to implement this method. What should it look like? If this should return an integer, he would put return 0. That would be an archetype of the answer. If it returned a string, he would return an empty string, or he would return none. If there was a particular exception that was characteristic of that function, he would put in arrays there. So for a getItem method, the abstract base class for it, the function would be defined as raise key error. Now this function is never going to be called, so all it is a template that says, when you write this function, it should take a key self, key, and if a key is missing, it should raise key error. In other words, it should give, you write this in a way that gives hints to the person that's implementing it. Doc strings are also fine for this purpose. I would say there is no standard and best practice here. Guido has made a model for us, and to the extent that works for us, it's great. To the extent it's not working for us, throw in all of your other tools. Put in a sample implementation, put in type annotations, put in doc strings. Do whatever you have to communicate. So I was a private pilot for a lot of years, and it was interesting the guidance they gave to us on talking on the radio. And roughly it was, always have a strong preference for standard flight language. So there's words like Roger and Wilco and immediate are words that have precise meaning to pilots. And then you layer in other words along the way that are just technical details. Exit runway 24 left immediate. However, the regulations are very clear. If communication is not occurring, you can switch to any other thing that works. And whatever you need to communicate works. So the example for that they give air traffic controllers is Cessna 385, exit taxiway 34 left, immediate. And then if you stay on the runway, they switch language. Get off my damn runway right now, you're about to be crushed by an Airbus 380. Nice knowing you. And so they will communicate in a very direct way. Likewise, the same is true of documenting abstract base classes. Say whatever you need to communicate to a person. Here's the method that you need to write. Fair enough? All right, great question. Thank you all so much again. It's an honor.
Thank you, Raymond.
By the way, I'm giving a tutorial tonight. The room holds 55 people. I hope you all come and crush us all in there. I'm doing 2 hours of lessons for you. It'll be intensive. You will learn a lot. I hope to see you tonight.